Okay, yeah. So we can use the old room as usual. Um,
Yeah, just pass me the link uh,
okay, sure. Actually,
in
in that case, I'll
in the
send you
chat,
I'll
maybe.
send you another link.
Okay.
Um,
Oh, no, in Messenger, yeah. Send the link in Messenger.
yeah, I've
Thanks.
been thinking quite a lot about just classical thermodynamics.
Uh, right.
Yeah, I actually get some intuition the uh about the Boltzmann distribution. Maybe yeah, I'll just share about it for now.
Hmm. What
You know
distribution? Ah,
how
the Boltzmann. Okay.
yeah, the Boltzmann distribution. So if a system is closed and yes, then there's with every there's a microstate distribution, meaning that every microstate with meaning every microstate with let's say the microstate is labeled by energy E, right? There'll be a few corresponding microstates. So for this E1, this perhaps this E2, and so this is known as the microstate distribution
Right.
uh omega of EI. So the key is that when you connect two systems together, their microstate distributions just multiply pointwise. So for example, if on the left over here, I have a microstate distribution which is 1331, and the bottom of 1112, right? Then they just multiply pointwise. Yeah, because microstate is number of micro the is the number of possible states for that given energy level, and yeah, and each composite system would have A times B.
Right.
Um, and and essentially what we're doing when we are connecting something to a thermal bath is we're connecting we're connecting a system, let's say omega one, to another system omega two, but omega two if it because temperature is defined as one over T equals to uh, derivative of um derivative of with respect to entropy with respect to energy, but entropy is K ln omega, right? So omega is a function of E and T is a function of E. So essentially, if the T on the denominator here is a constant, right? I'll just call it T bar. Then that leads to the solution that omega of E is equal to um exponential of E over K T bar. Right? This is the so essentially this is the requirement that a system has a constant temperature is basically the the equivalence an equivalent statement is that the number of microstates of the second bath would scale in this way.
Mm.
So when we connect the two of them together, if I imagine that the first system is something like maybe let's say the microstate distribution is even, it's just even across all equally equally distributed, right? Same number of microstates for all of them. There's no statistical preference. Then if the second bath looks something like that, where it's one, two, and four, and this basically is exponential eight, right? Essentially, what this does is, for each one of these microstate distributions, for each one of these macrostates, right? It kind of it kind of if I then multiply it out and I take a diagonal along here, it will look something like it looks something like 2, 4, 8, 16, and so on. So if I look at a diagonal, right, it seems if I constrain the total energy to be constant, um, if I constrain the total energy to be constant, essentially the composite system can move along this diagonal, and statistically it'll prefer the ones that occur most. So the ones that it'll tend to most, right, is the ones that have higher have higher microstates, and and these are the ones that are correspond to lower energy in the first distribution, meaning that initially we have yeah, I have a slide for this. Initially we have a microstate distribution omega one, but after connecting to a thermal bath, it gets attenuated by this exponential factor
Mm.
because the second the thermal bath essentially wants to suck away all the like yeah, it I think of it as sucking away all the higher energies statistically. Yeah, so there's just some intuition that I gained about the Boltzmann distribution.
Hmm. Uh, like maybe I'm oversimplifying, but it's important that like it's the form of exponential of the energy, so that if you add the energy, that leads to multiplication of the probabilities.
Hmm. Uh,
I think that's one way to deduce it. Um,
oh, um, I see, I see. So you're saying it's important for this, for the second distribution to have exponential or for the first
yeah,
one?
it could have never been exponential to e to the e squared. That wouldn't have made sense.
Yeah, yeah. Anyway, it's just some intuition I got for what connecting to a turbo bus kind of means. It kind of means you're connecting it to some system that has much more microstates in the higher energies, exponentially higher,
Yeah.
and as a result, it kind of sabotages your microstate distribution, assuming
Mm.
total energy is conserved.
Right. Yeah.
Yeah,
That
it's
that makes
exponentially
that makes
supported.
sense. Yeah. That's
Yeah,
how I
so
understand it. Uh,
okay, that's great. Yeah. Um,
uh, yeah. Um. Uh. For me personally, I don't know. I feel like I'm currently taking undergrad statistical mechanics right now. It's nothing new. Um, but I think like a lot of people just kind of over explain things.
hmm,
Um, but I think if you really look at like what's actually going on, um, it's not much. Maybe I could explain. So let's see here.
sure.
So I'm just gonna go right under the graph you drew. Um,
Sure.
so I think the thing with statistical mechanics, is that like, hmm, there's mainly two things going on, and one of them is the calculation of observables, and the other one is the second law. But the second law is only, in my personal opinion, in undergrad, the second law is only really described on a qualitative level, which is definitely understandable. But undergraduate statistical mechanics does make some pretty clear-cut statements about the calculations of observables. What we learned in undergrad class is that for a specific set of observables, we can calculate. Well, if it's a quantum system, we can calculate um its what it's we can calculate its expectation value. For a classical value, it would just be the value, and that this is equal um to, for the classical case, it would be the average of something over a probability distribution. For the classical case, it would be something similar.
Hmm,
And this probability distribution uh depends on what your system is. But what it's telling us is that for a variety of systems, um, as you take the limit where system size goes to infinity, you get a really good approximation, um, such that the error tends to zero. And this is due to
hmm,
basically the central limit theorem, in some sense.
yeah.
Um, and it also has, but not all systems follow this same property under the limit where the number of particles goes to the system size goes to infinity. For example, you could have non-chaotic systems or very simple systems, such that even for large system size, um, the motion is very predictable. I think a good example of this would be a system of gas but in which none of the gases interact with each other. So they literally just like move through each other. They never collide. There are no collisions. And you start with a system, a gas like this, that starts on the bottom left corner, and they all start moving in the exactly in the x direction. This motion will be very predictable, and the gases will never move upwards into this region at all. So you can't use the ergodic hypothesis in this case. So there are a lot of subtleties about for which systems you can use these types of ensembles, and things can also get subtle in cases like spontaneous symmetry breaking. But I think that's a whole another can of worms. The second thing that they teach us, before I move on, I have to note that many of another important equation that we learn in thermodynamics is that dW is PdV. But in the case of statistical mechanics, we can somewhat assert that P was basically defined as a quantity. That quantity being partial S partial V divided by partial S partial E. Or maybe there was a minus sign. Well, because d equals TdS minus PdV, and so basically, yeah. So we can assume that basically they defined it as so. But this is interesting because how do we know that the work done on a system, which can easily be defined just using ordinary classical mechanics? We don't need thermodynamics to define the work done. We already have work defined as a good quantity in classical mechanics. If you can scroll it down a bit more.
Okay.
So we already defined this. The question is then where is this formula coming from? Well, it becomes quite self-evident that if you work with the ensembles that are given in statistical mechanics using the above formula for the calculation of the expectation values of observables, and you understand the fact that the classical work is an example of such an observable in the case where you have a quasi-static process, then you can derive this formula quite easily using just statistical mechanics and the assumptions of the ensemble that you're using. So we're using the assumptions of basically a formula for calculating the expectation values of certain macroscopic observables. And if you just use that formula in just classical mechanics, you're able to derive this formula. And from here, you can think of the quantity called heat as something that becomes naturally defined in some sense. Because if we calculate dE, then from this formula, you can see that dE equals TdS minus PdV. So it tells us that in the general case, in the quasi-static case without heat, you wouldn't have this term. But if there is heat, then you would have this term. And the definition of heat comes naturally from the definition of work defined above that was necessary in proving this theorem. We can see that in order to prove this theorem, we have to basically assume. Wait, I'm having trouble connecting to the server. Okay, now I'm back. So we have to assume that there isn't any energy to get the above formula for the work. Well, okay. So for dE to be minus PdV, this is only true if there is no. Well, I'll say it in a different way. This is only true if everything. By everything, I mean energy transfer between the two systems happens very slowly and steadily. So this gives a natural definition of heat as energy transfer due to non-slow and steady change. And we can see that for a quasi-static process, this is just equal to TdS. So like these types of formula, could you go lower a bit? And like these formulas, basically the entirety of like these types of calculations in undergrad statistical mechanics just come from a formula about using ensembles to approximate the expectation values of certain observables in systems in the large N limit. The thing is, in the large N limit, this only applies to certain types of systems and certain types of observables. But the extent of which these techniques can be used is never really explained in an undergraduate class because it's still a very active field of research, such as ergodic theory, chaos theory, quantum chaos theory, and such. And to really study these fields, you have to use first principles. So you need the first principles of basically density matrices and Hamiltonian time evolution and such, and you have to work from there. And you have to probably use some statistical mathematical knowledge as well. And this obviously has had its crossovers with computer science as well.
What kind of research is going on in things like ergodic theory and do you
Honestly,
roughly know?
I don't know, but I think like just searching the archive would prove to be helpful because these fields would be easier to approach than string theory in terms of prerequisites. So yeah, you could check that out. The second part is the second law of thermodynamics, which is basically saying that a quantity called entropy increases with time. But you have to understand that the entropy has been defined using the ensemble, which we have used as basically a tool for calculating observables. So defining entropy in a totally arbitrary system is a bit of a difficult thing to do. If we were to define the fine-grained entropy, we would just define entropy as the von Neumann entropy, trace rho log of rho, where rho is the density matrix for a quantum system. This is the entanglement entropy, and this is totally well defined. But in the thermodynamics and statistical mechanics case, we're not calculating the entropy with the exact density matrix. For example, if you have a classical system, there's only one exact state at a particular time, so the entropy would have to be zero. But we get a non-zero entropy, and this is because we are calculating using a coarse-grained density, a coarse-grained state. So if we're going to discuss the increase of entropy, then obviously we will have to define the quantity that we call entropy. But defining entropy in the general case has to do a lot with what we mean by coarse graining. So how we even define the second law of thermodynamics is a bit of an active field of research. This is also being done with things like quantum chaos theory, ergodic theory, and so on. And also
what's the second word you said? What theory?
ergodic,
Ergodic, right? Okay,
yeah, etc., etc. Like I haven't studied these fields, but basically, we don't learn a lot about what's going on in undergrad stat mech. So we only really get a qualitative sense of what's going on. So that's really all I had to say. So
I see. Thanks for sharing.
Yeah, and that summarizes basically all I know about statistical mechanics at this point.
I see. Do you have any intuition for the free energy?
I think
Because I've been
it's not intuition is not really necessary. You just need to be good at calculating what should we call it, what transform, the with some trans yeah,
the
you just need
Lagrange transform.
to be nifty with partial derivatives.
Well,
Trying
I
to
mean,
the
I do
intuition
know
doesn't
how
really help.
I do
Well,
know how to calculate certain quantities like the IDF is and all those kind of things, but I'm a bit confused with how it ties in with the the statistical definition, which is minus kb t ln z, the partition function. So there's a few like equivalent. I'm not sure. I think this is only the thermo limit, the thermodynamic limit. Uh, I then there's a few others like I'm okay. This goes hand in hand with z is equal to e to the minus beta f. But then at the same time, I'm confused how this definition relates to the usual definition of the partition function, which is the sum over all microstates. So like there's a lot of yeah, I'm struggling to see how this connection as well as this connection from this. Yeah, from here everything kind of follows, but that's more classical. Like that, I'm a bit more confused about the statistical side where they
well,
define it.
the first thing you have to do, I think this is really important, you have to define your ensemble. If you define your ensemble, all of your assumptions and basically all of the vague parts are swept away in your definition of the
I
ensemble
see.
because you are basically postulating that your system is well defined by the ensemble. Well described by the ensemble. And by that, I mean that basically you can calculate some observables using the ensemble. So I think that's important. So define the ensemble,
Mm,
and for them, there is all calculations. Um, so it depends on whether or not you're using the microcanonical or canonical ensemble. Um,
mm, I see.
like
Suppose you're
technic,
using the micro.
yeah,
Um,
but you
yeah.
can
Suppose.
only use if you're like in an isolated system.
Right. Oh, so in some sense, if I define micro, there's no free energy because there's no temperature, right? You're just at a fixed energy.
Well, you could define temperature, but like those types of questions are just kind of too abstract. And like what's really going on is that your actual system will usually have some kind of heat transfer with the outside world. And like in that
Mm,
case, it would usually be more reasonable to model it as the canonical ensemble.
I see. So in the canonical ensemble, I did see somewhere where they said I looked at Blundell textbook and
Yeah.
they said something like the microcanonical ensemble is described by the the microstate distribution, and then the canonical ensemble is described by like Z, and then the partition function, and then grand the grand canonical ensemble is described by like the curly Z. Yeah.
Yeah, I
So
mean, yeah.
I'm
That's just being fancy.
I see. Mm, okay, perhaps suppose you're working in the canonical ensemble. Is it possible to show that these two relations are
It,
consistent with each other?
in the canonical ensemble, you would define the free energy as the formula, as the
Okay, sure. So
logarithm of
you
z.
define it as this.
Yeah.
And Z is defined to be this too, I suppose.
Yeah. Okay,
I see.
let me
Right.
actually do a derivation of something. I think I know what you're wanting. I'm just gonna write
Hmm,
something below that. Okay,
sure.
so like so if you have z, it's basically sum of e to the bei.
Mm-hmm.
We define S as the usual Gibbs entropy. Um, so this is going to be sum over what? BEI. Let's see. It's going to be we just it's going to be 1 over z times sum over e to the minus BEI, open parentheses, and then you're going to have to calculate BEI plus log z. This
Okay, so
follows from this is the
this follows
definition.
from
This is the definition.
KB ln Z2, right?
No,
Oh, it doesn't. Okay,
yeah, this is defined by the Gibbs entropy, which is basically given by
sure,
the sum. So sum over pi log pi.
sure.
So these are all definitions. And we can calculate u. Uh, we're gonna define it as like the expectation value of the energy, which is gonna be given by ei like that. Um,
Mm,
and then what we're gonna do is we're gonna define. Okay, I'm gonna take kb equals 1 because I hate the Boltzmann constant. Well, I don't hate it, but
mm,
it's a bit unnecessary. So we're going to define f as basically u minus ts. Um, so which is just also I don't really like t. I like beta. So this is u minus s divided by beta.
mm,
So we define these so we can just calculate. And this will be equal to basically sum over. Oh wait, I forgot to put 1 over z in front of you. So this is going to be equal to 1 over z times the sum for e to the minus beta ei. Then we're going to do they cancel and we get log z minus log z over beta. Uh, and this basically just can't the two of these cancel. This just gives us minus beta 1 over beta log z.
I see. Okay, so this is the Gibbs definition of entropy, right?
Yeah.
Um, um, would it be right to say that among different ensembles, there's different definitions of entropy?
You just use the Gibbs.
I see. Is it always the Gibbs?
Yeah.
Um, I see, I see. Because the one I'm familiar with is the one at least that I have been able to reason with myself is the K log Z one. So
You should
yeah,
use the
well,
Gibbs. You should
use the Gibbs.
definitely use the Gibbs, and the reason why it's crucial you use the Gibbs, and I'll explain why if you lower a bit.
I see, I see. Then is there any way to tie in with this K log Z? Because um
Well, you shouldn't use Lindsay in this case.
I see. Okay, sure, sure.
But like I mean, a lot of things end up being similar in the thermodynamic limit. So in that case, it
I
doesn't really
see.
matter.
I
Um,
see. Okay.
Different people approach the subject differently. If you're in the large numbers limit, then like all the ensembles give the same result, and this is super
I
easy to
see.
prove. But the thing is, so some people just like decide to never really clear things up about how things are maybe differently defined for certain ensembles, and they're just like, oh, I'm gonna give you a bunch of ensembles, they all work, just stick with it, just go with it. And like that's one way to teach it. Honestly, like, and it definitely works because in the thermodynamic limit where these ensembles are supposed to work, they end up being all the same, so it doesn't really matter, right? But at the same
Mm,
time, you might have a very small system, but that is still there is still like well described by one of the ensembles for some reason other than like thermodynamic reasons, right? But that system may not be described by the other ensembles because it's small. And this might happen, say, for the Unruh effect.
I
And
see.
like other cases in physics, where sometimes some ensemble just magically appears not due to statistical reasons, but due to dynamical reasons or whatever. Um,
I
so I
see.
think it's
Okay.
more prudent to teach each ensemble separately. And
I see.
only, yeah, so like, so the reason why you have to use the Gibbs entropy, and this is super duper duper important, is because as I said, dW is equal to partial S over partial V over partial S over partial E dV, right?
Mm-hmm.
Um, Now let me tell you how you prove this. You can say that the Hamiltonian is a function of the PIs and the QIs and V, which is like a parameter. It's not a dynamical value. Um, for example, if it's like a box, right? If it's like a
Mm-hmm.
box, then there is a well potential with infinite
Mm,
energy of the well, and the size of the well is given by V. So this is a parameter in the Hamiltonian. Um, and you can see that basically dW, right? We define dW physically as dE when basically dE when dE can be well approximated by partial H over partial V, the expectation value of partial H over partial V dV.
mm.
So we calculate partial H over partial V. This is done using the ensemble formula, right? So this would be equal to 1 over z, right? And then just a sum over e to the minus beta ei partial H over partial V.
Mm.
Um, and if you just use this formula, you can see that you get the formula coming from the entropy. It's not really that hard, but it's only true when you like use the Gibbs entropy. So like uh wait, I have this problem where I accidentally press the back button on my tablet a lot, and it like I have to re-enter every time, and it takes some time to look. Okay, so I'm back in. Let's see. So I think like this was in like one of the exercises in physics with Witten. Um,
Oh,
so what you get is like from here you can naturally derive. This is an exercise for the viewer. You get like you get this. But you have to use the Gibbs definition of entropy.
I
Super
see.
duper important. And this is why you should use Gibbs. It gives the correct formula for the work. Um,
I see. I see. Okay. Um, I am seeing I'm seeing this statement they mention in the entropy Wikipedia where they say that this the various ensembles in StatMech are linked to the entropy via the following relations. But this is from the Gibbs entropy uh the the Gibbs entropy
yeah,
page. Yeah, I'm a little bit confused by what they mean by this statement.
it's just a calculation of Gibbs entropy for each ensemble.
I see, I see. So in some sense, oh, I understand now. So the K ln omega, that was the that was what we'll get if we applied the Gibbs entropy formula to the microcanonical ensemble.
Yeah,
I see. Okay, that makes a lot of sense. So the Gibbs entropy is the mother of all formulas for all the entropies.
yeah.
If I'm remembering this as the definition, then
Oh,
I'm only
because
defining, yeah,
there was a box. It's a good box. If you go up a little bit, um,
this box,
go up a little. Yeah,
this one.
yeah. This box
I
is basically some more or less equivalent to the proof I was just talking about.
I see.
So yeah, Wikipedia is like pretty nice in this case.
Mm.
And I
Um,
would say that all like the canonical thermostatic textbooks like Blundell and Schroeder are too old and thus very
I
overrated.
see. I see. I see. Sometimes I'm a little bit hesitant to use the definition of the use of like work and heat and stuff and volume because I'm thinking of trying to understand StatMech with as a more general framework that applies to things like magnetization and things like that as well. So
Like things like what?
magnetization and yeah, like I'm a bit hesitant sometimes to invoke the work work and work and like volume and pressure, this kind of quantities, because to me
I mean,
those
like
are
you can abstract those. I do.
mm,
Like because like
I
if you
see.
don't work with like an abstraction of work and heat, it's annoying because like there is no there is no model for a steam engine. You would have to define all the interactions between like the valves, like the molecules and the valves and stuff like that, and that's gonna drive you crazy.
Mm,
You would have to work with abstractions. I should write like a statmech, like a short statmech document for mathematicians. I think that would be nice because
I
like
see.
a lot of math folks have no idea what physicists are doing because
Mm.
I think the main reason for that is physicists don't know what their physicists are doing. But like, yeah,
Yeah. I see. So okay, so when we talk about system that doing work on the environment, things like that, like I guess my main concern about this work thing is if I have a box of spins, let's say the icing model, it doesn't really make
yeah.
sense to say that the icing model does that has a pressure and does some work PDV on the environment or things like that. So would
It
that
only
case,
makes sense if there's like some parameter, some macroscopic parameter in the Hamiltonian.
right?
For example, a
I see.
magnetic field, like a magnetic field, external magnetic field. That is for sure external parameter if you're not considering quantum electrodynamics and like electromagnetic wave propagation. That's
Mm,
definitely an external variable. Or
I
if you have an
see.
external potential, right, in the lab, that would be a very good model of an experiment you could actually do. If you have an external potential and you could like change the value of that potential, um, that could be an equivalent of volume, and there would be an equivalent of pressure for that. Um, and I would honestly say that unless you're an engineer, most of the physical systems that people are dealing with in the lab have an analog of pressure, not actual pressure. Maybe
I see.
because like
I
it's
see.
modern and it's cool, right? Like,
Mm,
yeah.
I see, I see. That's cool. Um, yeah, I see. All right. Yeah, and then there's a story of all the inexact differentials and all these kind of things. I think that's just a matter of um understanding uh
Oh yeah, it's just the wrong
yeah,
cohomology.
yeah. Correct, correct. And how about
Yeah.
maybe if you could talk a bit about black hole thermodynamics because
Oh yeah,
I've
sure.
been yeah, I think that's something that's up your alley and you probably uh, know
Okay.
quite a lot about that.
this is a this is a topic that okay, so a lot of people have lots of opinions on this one. Okay, let me talk about stuff that I would want to talk about. Okay, so let me just try it out. Okay. Um so um where do I start? So it's known there's a formula apparently that like black holes have entropy equal to the area of their event horizon divided by some constants. I don't care. But like,
Mm,
I mean, sometimes you should care when you're like talking to the experimenters. But in this case, you can use dimensional analysis to figure things out. Obviously, it's the square of the Planck length, right? Obviously.
mm,
But like anyway, like yeah. So, but the question is why and how do we derive this formula? Uh, you could derive this formula as follows. There is something called ADS-CFT, which is okay. So it's
mm,
ADS-CFT from the most conservative way to say ADS-CFT is there is a quantum field theory. This is something that has the slightest well that has well okay so this is something that has a possibility of being mathematically rigorously defined. Quantum gravity there is no possibility, but for quantum field theory there is a possibility we could define quantum field theories. That makes sense in the case of ADS-CFT because people are interested in the Yang-Mills mass gap problem. And
mm,
somebody might argue that it's more easier when your Yang-Mills theory is supersymmetric, because then it's a superconformal field theory. And that's exactly the field theory that's in ADS-CFT. So yeah,
mm,
I feel that if mathematicians might be encouraged to rigorously define quantum field theory here. And they say that there is a duality between this and a quantum gravity theory. Um,
okay. So sorry, I was just very intrigued by your statement on the Yang-Mills mass gap. Actually, after studying physics for so long, I've never quite understood what's the significance of solving Yang-Mills
oh,
mass gap.
okay, so I can definitely exposit what's going on because this is one of the things I'm interested in. Well, no, I mean
I
I'm not
see.
interested in solving the Yang-Mills mass problem. That's just way too hard. But I'm interested in like so the thing is you have a quantum field theory. So you can do you have so the thing you can consider is that you have free fields, and free fields are those
Mm-hmm.
without interactions.
Mm,
In other words, the action is basically harmonic in the sense that it is.
mm,
And then you have interacting QFTs. So you can have like phi squared, phi cubed, phi, etc., etc. Um, so the thing is about this, the interacting QFTs have so free fields are super duper easy, at least compared to the interacting QFTs. There
mm,
are still some non-trivial math that you can do with free fields, considering free fields in curved spacetime, and that has a lot of things related to functional analysis going on. That's kind of
mm,
cool. But
mm,
that's more of an analysis problem. But like free fields can definitely be rigorously defined.
mm. So rigorously defined as in the QFT is rigorously defined in terms of the Whiteman axioms and stuff.
It's not really about axioms. Like for free
Oh,
fields, you just need like a you just need a very simple understanding. And by simple, I mean just an understanding of separable Hilbert spaces. If you want to do
I
it with
see.
yeah, so it's like
Okay.
it's super doable. It's just there are a few non-trivial analysis problems, but even those problems are well defined, very approachable. Witten is working on similar things. But those
I see.
problems, in my opinion, are kind of not fun. The really fun
Mm,
problems always have to do with topology, and those problems
see.
aren't really so like okay, so like interacting QFTs. This is super hard. This is kind of hard to rigorously define. In general, like it's really not being done. Um, but you can rigorously define perturbative QFT. See Kevin Costello's book.
Mm,
And many people agree that you could rigorously define perturbative string theory as well. And like these, like because like perturbation theory, um, from a mathematician's perspective, perturbation theory is really about um giving some mathematical information to like a series of diagrams, Feynman diagrams. And that is a much simpler problem than defining the quantum field theory in full because there are non-perturbative effects. You
mm.
might have to scroll down a little bit.
Oh, by Kevin Costello's book, you're referring to the renormalization and effective field theory, right?
Yeah,
Okay, sure.
non-perturbative effects, and this is exactly the effect that's in the mass gap. I won't go into detail about this, but the mass gap is a non-perturbative effect in Yang-Mills theory. So
I
basically, if
see.
you want to understand the mass gap, you have to come up with a mathematically rigorous definition of Yang-Mills theory, um, non-perturbatively complete rigorously definition of a strongly interacting quantum field theory, and that's why it's such a big problem.
I see. And why do people and why is it significant? Is it because in order to obtain the rigorous proof for why the mass gap exists, you essentially need to develop interacting QFT completely?
Like you can't even like the problem is twofold. Like the literal mass gap problem is two problems. You need to show that Yang Mills exists and that it has a mass gap. So you to show
Mm,
that Yang Mills exists and like satisfies the Weikman axioms, you basically have to define it.
I
Um,
see.
I don't like to talk about things like Weikman axioms not yet because there could be many equivalent there could be many different ways to approach like the formalization of QFT, and any really old ways to do it might be a bit outdated. The way
I
people
see.
think about QFT have evolved like so much in the past decades, and like I think Witten is probably the person who has the best understanding of what QFT is. Many physicists who are basically just calculating hard calculations at this point. Witten seems to have a good idea of what's going on. Some mathematicians who are into mostly like topological geometrical representation theoretic aspects of it. So like that's the stuff that's going on. Um,
I
but
see.
yeah, but like back to black hole thermodynamics. What I was saying is that
Oh yeah.
by quantum gravity theory, people are talking about a non-perturbatively well-defined theory of string theory, or some other quantum gravity theory. These things are a very far away milestone. It would be so hard to rigorously define what that means.
Mm,
Um, Currently, I think physicists have given up a bit. If you look at people doing research in quantum gravity, what they're doing is they basically start off with a quantum field theory calculation, and they see that some of these calculations are similar to differential geometry calculations. That's essentially what they're doing.
mm,
They're not defining
I
a
see.
quantum gravity theory. They're doing quantum field theory calculations and saying that these calculations are a little bit geometrical. So what's really happening in physics research these days is you do a quantum field theory calculation and just kind of argue that these calculations seem to resemble something like a black hole or something.
I see.
But what you can do is you can calculate the entropy here,
Mm,
And it has been shown that these calculations do match the black hole entropy formula of
I
like
see.
proportional to the area. And that's black hole thermodynamics. It's not a very satisfactory explanation, but it is what it is.
What would entropy in QFT be defined as? Is it the Gibbs
Von Neumann.
definition? The von Neumann entropy. Okay,
Yeah.
I see. Cool, cool. I see, I see. All right. In that case, mm, then there's all the mention about uh like there's the like what are the thermodynamic potentials of a black hole?
Yeah. That is, I mean, if you know the like, it's the same thing as the thermodynamic potentials of a quantum field theory system, to the extent that has been researched. And like a quantum field theoretic system is just a system. Like, so I don't think that's a
Mm,
very difficult question to the extent that's being currently researched right now. Um,
I see.
any any research done of quantum gravity that does not use holographic duality will be a little bit fishier, and the rules will be a lot more uncertain.
I see.
Like I'm not saying that loop quantum gravity is wrong. But they're probably doing things that are important, that are pretty cool. I'm saying that the calculations done over there, really just feel like calculations. I mean, a lot of physics research that is a little bit too speculative do feel this way, but they're doing calculations and they're interpreting the results. But whether or not these interpretations can be justified, a lot of times it's an open question. Like for example,
Mm,
the paper a few months back about the wormhole in the lab. No, they did not make a wormhole in the lab. What they did was they did some calculation on a quantum computer, but they said that you could interpret that as a wormhole. So the subtlety
mm,
here is in interpreting a calculation. But the
mm,
physical interpretation of a calculation, sometimes this subtlety um, can be abused to give a very cool interpretation to a calculation. But at the end of the day, we really have to be kind of honest about what we're doing.
mm, I
Yeah,
see.
that's what I wanted to say anyway. That's my opinion on the thing. I'm trying not to have a very specific stance on this because there's still a lot I have
Mm,
to learn. But it seems that
mm,
like
mm.
a lot of what's happening has to deal with doing a calculation and interpreting it.
Yeah, I see. Okay, cool, cool. Yeah, I know last week I promised to teach to explain the uh quasi probabilities, but it's been a while since I touched that. Um, yeah, do you know anything about it, or shall I try to just briefly mention something?
Is it like statistics?
Yeah, quasi probability in terms of in quantum mechanics,
Uh,
the Wigner function, if it rings a bell, the Wigner quasi probability, this one, something like that.
that one. Yeah, yeah, I know, I know.
I see. Do
It's
you have
like a
anything?
pseudo distribution.
Yeah, it's a pseudo distribution.
Right.
So,
I talked about like me possibly doing something on the Wigner measure or something, but like that
oh
maybe that's
yeah,
for next week.
yeah,
This
okay,
is
sure.
this is just like something about quantum mechanics. Um,
Mm,
like maybe next week I will be talking about attempts to rigorously define path intervals using measure theory, and the reason why these
sure.
attempts do not cover the whole story.
I
Because I think
see.
it's important. Yeah, maybe
Okay,
I should do measure theory next time. Measure theory is really important.
sure, sure. From what I understand from the Wigner function, I don't know all the calculations in great detail, but basically the defining probability distribution that can be negative. Um, and the reason why that might be allowed is because if you have some negative region, and if it's surrounded by some positive probability region,
Mm,
in and this is something on phase space, so P and Q, or in terms of like if you're talking about optics and stuff, it'll be creation and inertial operators or things like that.
yeah.
And roughly speaking, phase space when it's quantized, you cannot know precisely the position and the momentum, right? So when you do a measurement you can only measure over some region, some fuzzy region.
Yeah.
In some sense, you can only know that it's within this region. So if you know the particle is within some region like this, the net effect is that the overall probability is positive,
Mm.
even though there's negative region over here, because you can see that there's no way to cover the negative region with something of area h bar
That
without
makes sense.
without being the probability without touching the positive regions. So that's roughly all that I know about it at the moment. Yeah, I was trying to study it for a while, but I think I hit a roadblock somewhere, but I forgot where.
Yeah. Yeah, that does seem interesting because right. Yeah. I'm also trying to. I'm trying to work on talking about um supersymmetric quantum mechanics rigorously
Mm,
in a few weeks. Um,
I see.
then
How's
later
your
on along the road, I might talk about topological quantum field theory
cool,
rigorously,
cool.
maybe in the abelian case only. But and then a few days later, I might talk about sigma models, free conformal field theories. That's another topic
Mm,
that's really cool, but I can talk about rigorously, and it's a good place to start heading towards mirror symmetry rigorously.
I
And by
see.
rigorously, I mean like both from a total mathematical proof and an attempt to understand the physical proof rigorously. And I guess
Mm,
I'm trying to understand things both from the math aspect, which is super duper important, but also from the aspect of taking the physical proof and trying to make it a lot more rigorous. This usually
mm,
requires a lot of analysis, but in this case, the analysis is really worth it. So I think, yeah, I'm trying to do that.
mm. Cool, cool. Oh yeah, there's something something are you familiar with the tenfold the real classification of topological insulators?
I'm not familiar. I'm not sure if I'm interested yet.
I see. Okay, but it's just I just wanted to share there's a very nice talk about this by on YouTube by it's just called tenfold. The video is just called tenfold classification. I think it is it's by yeah, it's just this video, the first video, John Bass over here.
Hmm.
He talks about it's basically a statement about a classification of Hilbert spaces with respecting certain symmetries like the C, P, and T symmetries.
Hmm.
Uh, I think it's mostly C and yeah, I'm not too sure, but it's just something about the tenfold classification comes naturally from the classification of Hilbert spaces, and it's quite mathematical. Um, but what's interesting is that there are certain classes. So the tenfold way classifies all the topological instances into different categories, into different um sectors, and each sector will have a few examples, right? But recently, or rather not, well, not recently, but there has been some realization that even though the tenfold way might classify two condensed matter two theories as identical in this tenfold classification, there
Yeah.
is a sub classification among it, and one of them are examples of Hopf insulators, where basically the locus in K space where the bends touch, right? In condensed matter physics, we are concerned about when the bends touch. For
Yeah.
example, if they touch over here and they might touch again over here in three-dimensional space, this would be some curve through uh, this is K, this is just K, this is one-dimensional space, but in three dimensions you can imagine that the K space might be it might be a curve or a surface through K space. Um, and it turns out that that curve through K space, that curve can can possibly tie into can possibly have knots. So you can possibly things like
Huh.
uh yeah, so that's something that is of interest over here. Something like that. Yeah.
That's interesting.
So
I would.
you can actually classify you wonder
I wonder if it has any use in proving mathematical theorems.
um I'm not sure about that, but it does lead to an uh interesting questions you can ask about condensed matter systems.
Hmm.
And for the tenfold way, there's an effective field theory written in terms of Chen Simons and topological field theories.
Yeah.
right? But then I don't think there's an effective field theory for Hall of insulators yet because it's still quite new.
Yeah.
Um, yeah, so that's something that might be interesting because yeah, building effective field theories for such systems just seem like a pretty fun thing to me.
Yeah, this does sound fun.
Yeah,
Although these
but I
days,
don't know enough
like
to do
I've came up with this strategy
Mm.
to just study the math. I don't know, like I'm really going the math route. And the reason why is because like when you study like how a physical system is mathematically described, I don't feel like I learn much. It's just like
Mm,
trivia. But if I learn
mm,
how the
mm,
math works, that makes me smarter.
mm. Yeah.
And I just want to get smarter because if I get smarter, I can do a lot of fun things. Um,
Mm,
Although I am working on a physics problem right now. That's one of the things I'm doing. But I feel like in physics, the most important thing is that you really have to understand if your physical assumptions are well justified. I think that's the thing
mm,
that a lot of people aren't really talking about. They're too eager to just talk about what they came up with. But I think like whether or not that can be justified, not
mm,
and like that question of whether or not that it can be justified is not a problem of mathematics. It's really a problem of physics. And I feel like these types of thoughts are really well thought out by the experimentalists. So I'm not sure if the theorists are really good at it. See, the
I
problem
see.
is not too much math in physics because there can never be too much math. But the problem is too little physics, and too little physics does not, and basically means that the theorists aren't really talking about whether or not their physical assumptions can be justified, as well as experimentalists and especially phenomenologists do. So they really have to like kind
Mm,
of learn how to do that. Like yeah,
I
I
see.
suppose.
I see. Yeah. Okay. Cool. Yeah. But for example, I think the top of, I think the magnetic monopole, it really doesn't make sense if we do not know enough math about line bundles and
Yeah,
whatnot. Yeah, it just doesn't really hold.
yeah. But then again, like
Yeah.
if you start studying math solely based on its relevance in physics, you might have a really terrible math background. Because to do math, you need to do
Mm,
like the canonical
mm,
background for math, and that does require a
mm,
healthy dose of category theory,
mm.
algebra, and
Right.
analysis. All three of these, all physicists just end up doing a lot of geometry. Um, but
Mm,
even in geometry, just by doing geometry, you can't really go a long way. You really need
I
to know a
see.
lot of analysis to do things in geometry, but physicists aren't even doing that. So you end up, if you really just keep going down the physics math route, you just end up doing just a bunch of basic geometry, and,
Mm.
and that's not good. So yeah.
On that note, I would like, if you're talking about category theory, there is a book that I like to recommend about it. It's called Category Theory in Context by Emily Liu. Because this book is good and it's yeah
Could you
it's a
like
good book.
show me a page? No, show me the
Sure,
table of contexts. Let me see the vibe.
sure.
Uh, a bit later on.
It's a very mathematical though.
Yeah, a bit more.
Um,
That doesn't seem too bad. Right now I'm just trying to like study kind of restrict to abelian categories and just study uh homological algebra because that
I
seems the
see,
most relevant to me. I'm not a fan of going too abstract. Um,
I see.
I will use abstractions as necessary, but like starting from the
Mm,
abstractions that feels too detached to me.
I like this book because it does give you quite a lot of context for why we define things a certain way.
Yeah.
Like
I mean,
over here they
I do like to just start from definitions and work out why they're useful. But like I only do this when I know that the end result will be cool. Um,
I see.
However, I'm not a fan of like being well motivated but not knowing where I'm going.
I see. Okay, yeah. Um,
Oh yeah, thank you for the
yeah.
recommendation. I'll probably read the book out of context. Like, yeah, it'll be helpful.
Mm, yeah. If not, thanks for yeah, this session. Is there anything else you want to share?
No, I think I'm good.
Okay, sure. Thank you. Yeah.
Yeah.
Have a nice day.
Yep. Thanks.